Hello, this is James Xiao. This is my second lab for PHYS2211, and it's going to be about freefall. And so the purpose of this lab is to demonstrate an object's motion in freefall due to gravity. And we're going to analyze the position and velocity over time of the object and compare it to a computation of the object falling. And in this lab, we're going to demonstrate the momentum/velocity update formula as well as the position update formula. And we're demonstrating our knowledge of how gravity works at the surface of Earth, and how the net force works as well with that. And here's a quick preview to my results, and they will shock you. So what I used in this lab was an iPhone to record my experiment, my Piplup Squishmallow tag that fell off, and myself. And so here's how I conducted the experiment. I just held the tag above my head, and I just let it fall down to the ground, and I used tracker to track all the as it fell down. And so here are the forces that act on the object. We have gravity, demonstrated by this apple right here, and we have air drag, air drag/air resistance, same thing, demonstrated by this parachuter. And so here are the results from my physical lab. To the top right, we have my position versus time graph, as you can see, pretty curved, that's good. And then my velocity versus time graph, which is close to a straight line, but not really. And also, there's it doesn't move here because I just held above my head for a couple of seconds, for like a second before dropping it. Don't worry about that. So basically, motion starts at 1.14 seconds. And the reason why velocity is straight is because gravity is gonna be 9.8 the whole time. So velocity, according to the velocity update formula, is gonna update by that every change in time. So it's gonna be like plus 9.8 plus 9.8 plus 9.8, which will mean it's a straight line. And now the reason why the position update formula is curved is because it uses the velocity to update itself. And since the velocity is getting bigger, it's not constant per change in time. It's gonna get bigger, which creates the curvedness right there. And so how does my experiment compare with a computational model of it? And if we zoom in here real quick, we can see that my computational model actually goes a little bit further, and that makes sense because in real life there's drag, which will cause the object to not go as far because it is a force acting against gravity, which means, yeah, you understand. And so how does my second computational model compare with my experiment? Well, as you can see, it's actually less than the previous computational model and also less than my experiment. And so that makes sense because the drag will work against gravity, meaning it will just go less far. And I'll explain more about why it's less later. So here's a graph of all three of these models together. As you can see, they're all pretty similar. So we have blue, which is our computed gravity plus drag model. Red is what I tested it, and yellow is just only gravity. And so here's how I did the code. I'm gonna zoom in here. I'm gonna zoom in here, but this is a segment t less than 2. This is the same as you can see, but it's all set to 0. This is the important part though. And so how I calculated with drag is I did this using this drag formula equation that was given to me, and I did that times the delta t because yeah, makes sense. And then for just normal, I would just comment this part out. Velocity update formula, I used this velocity, that, and then for the position update right here, I used this formula. But I actually used V final instead of V average because I actually don't know how to make V average. So yeah. And so some possible errors that happened in my experiment. I didn't hold the tag completely still above my head, so that wasn't perfect. Also, I didn't track it perfectly either. And another error is that in the equation for air drag, I don't know what B actually does, so that may have messed up my calculations. And since I didn't know, I didn't include it. And yeah, I use V final instead of V average because I don't actually know how to do that. And then finally, what does it mean? What if, basically what I'm trying to say here is if, the model with air drag will have a terminal velocity because, at some point it's gonna develop, what is it? Since the air drag is based off the velocity, it's gonna at some point get big enough so it equals the gravity, and so that will have a net force of 0. And then, I'll show you this way. If you have another force, then you can actually have, velocity greater than the terminal velocity, but as soon as that force goes away, it will equal out. There's a bit more to that, but my time is pretty much up, and just pause and read what I say here. Yeah, that concludes my experiment. I hope you guys liked it. Please give it a 100, please.